Hey guys, a very warm welcome. In today's discussion, we are going to discuss about retrievers for RAG for reasoning tasks and how can we train these retrievers for reasoning tasks. And this is inspired through a research on natural language processing from from Meta's AI engineers team. And I will be sharing this URL with you. You can download the paper and have an understanding. So I'll give you a quick brief about what they have discussed. So basically, this Meta's, ReasonIR article, it typically introduces ReasonIR 8B. It is a retriever which is built specifically for reasoning heavy RAG systems. And normal retrievers are good at simple factual search, where the answer is directly written in a document, but they struggle when the question needs background knowledge, indirect clues, or multi-step thinking. So ReasonIR solves this by training the retriever to find documents that are useful for reasoning, not only documents that match keywords. So in this article, basically, they have discussed a Bi-encoder retriever, which typically converts the user query and each document into embeddings and then retrieves documents using similarity scoring. And for this similarity scoring, they use cosine similarity. So the process is like this. You have a query, you will convert that query into query embedding. Then you have a document, you're going to convert that document into document embedding. Then we run a similarity score through which we fetch the top documents. And the retriever formula which is used is a cosine similarity formula with inputs as query embedding and document embedding. And finally, we are going to get a score and a distance. Okay. So this model is trained using contrastive learning, where the query is pushed closer to the correct useful document and pushed away from confusing but wrong documents. So the key training pipeline is called ReasonIR Synthesizer. What it typically do, the code which I'm going to discuss today will generate certain training data type, which would be a public retriever data where we have normal Q&A retrieval data sets, and it matters because it gives general search ability. Similarly, we are going to have varied length queries in this training data type. These variable length queries would be short and long synthetic queries, and these will help models handle long reasoning questions. Similarly, we'll have hard queries as a data type. So in hard queries are basically used because difficult reasoning questions generated from good documents. So that is what hard queries does, and it helps train models for real reasoning search. And we will have some hard negatives. These will be the documents that look relevant but are actually unhelpful. And these teaches model not to get fooled by documents. Then we will perform query rewriting, where we expand user question into a richer reasoning query. And we are going to improve retrieval quality at test time. And we will also be implementing LLM re-ranking, where LLM reorders retrieved documents and improves final top document quality. So basically, the USP of this article is that ReasonIR is not just another RAG retriever. It is a retriever trained specifically to support reasoning. Okay. Most RAG systems fail because retriever brings shallow keyword matched documents. ReasonIR improves the retrieval stage itself by training on reasoning style synthetic data and hard negatives. And this makes it useful for advanced GenAI applications like research assistants, legal RAG, medical RAG, coding assistants, financial analysis, and interview preparation systems. So its strongest point is that it can outperform expensive LLM re-rankers while using much less compute. And Meta reports that ReasonIR with query rewriting outperforms recent re-ranker baselines while requiring over 200x less compute. So the important metrics which we are going to discuss in this would be normalized discounted cumulative gain at 10, which is generally called as NDCG at 10. So this will help us evaluate the ranking quality of top 10 retrieved documents. Okay. And this normalized discounted cumulative gain, it helps us check whether the most useful documents are ranked near the top. Higher is better. And ReasonIR gets 29.9 NDCG at 10 without re-ranker and 36.9 NDCG at 10 with re-ranker on Bright. So what is Bright? Bright is basically benchmark for reasoning intensive information retrieval. Okay. So what do we evaluate here? We evaluate the retrieval quality on reasoning heavy tasks. And this tests whether the retriever can find documents useful for reasoning, not just keyword matches. Similarly, we are also going to use a metric which is MMLU, which is massive multitask language understanding. This evaluates LLM performance across many academic and professional subjects. And this is used to test whether better retrieval improves final RAG answer accuracy. ReasonIR improves MMLU performance by 6.4% relative to closed book baselines. And we will also consider this metric GPQA, which they have discussed. So GPQA is graduate level Google Proof Q&A benchmark. So this evaluates like a very difficult expert level reasoning questions. And this is used to test RAG on hard questions where simple search is not enough. And ReasonIR improves GPQA by 22.6% relative to closed book baselines. Then we also evaluate RAG performance. So this is retrieval augmented generation performance, where final answer quality after retrieved documents are given to the element will be evaluated. And this evaluates whether better retrieval actually improves the LLM answers or not. So this will be evaluated. Similarly, we also consider this metric known as test time compute. So what typically this do? So the compute used during inference is this test time compute, and we do cost and speed of retrieval re-ranking during the actual usage. And ReasonIR is efficient because it improves retrieval without depending heavily on expensive re-ranking. We also consider hard negative error rate. So this is an error rate on confusing negative documents, and whether the retriever wrongly ranks misleading documents above correct ones. So this measures how easily the retriever gets fooled by documents that look related but are not useful. And we are also going to talk about recall. So basically, recall is retrieval relevant document coverage, whether relevant documents appear in the retrieved set or not. So higher the recall means the retriever successfully brings useful documents before re-ranking or answer generation. So this is what these are the metrics which we are going to consider. So now I'll take you to the Meta ReasonIR implementation code, which I have implemented in Jupyter Notebook on my Windows instance. I have installed a couple of libraries for this, and let me just quickly give you what libraries are installed for this. So currently I'm working on HV environment, so I have activated this. I have upgraded pip. PIP. So I have also installed these libraries: sentence transformers, scikit-learn, and numpy. These are the libraries which are required for you to implement this program. And then this is to utilize my appropriate kernel. So these are the libraries which you would be needing: sentence transformers, scikit-learn, and numpy. Now I am typically taking you to the code. So here we are going to discuss this basic ReasonIR-style RAG implementation. So this implementation is done inspired through this paper from Meta. So this code shows the core technical idea of the ReasonIR paper. And the reasoning idea is that a normal retriever may only match keywords from the documents and then fetch those documents, on the basis of those keywords, matching keywords. But a reasoning retriever should find documents that help answer a difficult question, even when the same words are not used and they are not available. So we're going to use this pipeline where we have a question. Then we are going to perform query rewrite, query embedding, document embedding, performing cosine similarity, filtering documents, and producing the RAG style answer. So this is what we are going to implement in this particular code. And I have also implemented this code and kept this code file in a public GitHub repo. And the link of this public GitHub repo is also shared for you to access. And later I'm going to verify this code for a production grade through CareerOS, and then we are going to modify this code to a production level environment so that you can use it for your targeted roles and targeted salaries, okay, in your resume. So so before that, I would like to give you a quick summary of what this code does. So this code implements a basic ReasonIR-style RAG retrieval system. It uses small document knowledge base and converts each document into vector embeddings using sentence transformers. Okay. So when a user asks a question, the code rewrites the query into a richer reasoning style query, converts it into an embedding, compares it with document embeddings using cosine similarity, retrieves the top matching documents, and then generates a simple answer using the most relevant retrieved documents. Okay. So the output typically shows that the system successfully retrieves the correct hidden concept for different reasoning style questions. For example, when the user asks why night shift workers struggle to sleep during the day, the system retrieves circadian rhythm as the top document with a similarity score of around 0.46%. For the question about an employee being fired after reporting misconduct, it retrieves wrongful termination with a score of 0.45%. And these I'm talking on the basis of the results which we have got on the basis of implementation of this code. Okay, here are the questions and here are the results which we are going to discuss. So in simple terms, what are we going to do? We are going to take a question from a user, a query rewrite would be done, then query embedding would be performed, then document embedding would be performed, a cosine similarity between this query embedding and document embedding will be done, and a cosine similarity score will be calculated. On the basis of these cosine similarity scores, top documents will be filtered, and then on the basis of those top documents, a RAG style answer would be generated. So in order to implement this code, I would like to give you the structure of this code. So what I have typically done, so initially the code is done in this way where we have imported libraries like sentence transformers, and in order to perform cosine similarity, we used cosine similarity. So these libraries help create embeddings and compare query document similarities. These are the two libraries which are used. Followed by we create document knowledge base. Okay, so these document knowledge base defines sample documents like circadian rhythm, wrongful termination, overfitting, and RAG related information. So the retriever needs a document collection to search from. So these are the typical 5 set of documents which I have created in form of JSON. You can consider any document, then you can convert it into a JSON format or however you would like it to be represented. So this is the sample document which I have taken. Then we have defined, the training examples where we create sample query, a positive document and a hard negative document pairs. And this helps us in showing the ReasonIR style training structure, where the model should learn useful versus confusing documents both. Okay. Then we perform, rewrite user query, where we expand the user question into a richer reasoning query. And I'm going to explain how that is done. We are going to perform reasoning questions, and these reasoning questions may not contain exact keywords. So rewriting helps the retrieval. Then as step number 5, we do load embedding model. And we load sentence transformer, all mini LM L6 V2. This is the model which we use. So this model converts text into numerical vectors called embeddings. That is what we do. Then we encode documents. So we convert all documents into embeddings once. And these pre-computed documents embeddings make retrieval faster. Then we encode user query. So we convert the rewritten user query into an embedding. So the query must also become a vector, so it can be compared with document vectors. So hence we encode the user query also. Then we perform cosine similarity calculations where we compare query embedding with each document embedding. And higher cosine similarity means the document is more relevant to the query. Then we rank these documents. So we sort documents by similarity score from highest to lowest. And this helps select the most useful documents for answering. Then when we retrieve these top key documents, we return the top matching documents with scores, and these documents become the context for the RAG answer. Then we generate answer. So we uses the highest ranked document to create a simple answer. So this simulates how RAG uses retrieved context to answer questions. And then we test sample queries where we run the system on 4 example questions. And this verifies whether the retriever can identify the right concept or not. And in the output interpretations, we have got around 4 user queries, which we would be testing and which we would be observing. So now, so here in the code, if I walk you step by step. So first, here are the libraries which we imported. Import numpy as np, and we imported sentence transformer. So this is to use sentence transformer to convert text into numerics. And the model which we use is all-mini LM-L6v2. And to compute cosine similarity, we are using this library sklearn matrix pairwise, and we imported cosine similarity, and this will help us score the query embeddings and the document embeddings. Okay. So later we created documents. So we have this document known as circadian rhythm, which has some text in it. Then we have corporate restructuring, which has some text in it. Then we have wrongful termination, which has some text in it. Okay. Then we have machine learning overfitting document, which has some text in it. Then we have retrieval augmented generation document, which has some 4 lines of text in it. Similarly, here is the training data. This is not full training. It only shows how ReasonIR style data is structured. So each training example has a query where we have a reasoning heavy question. Then we have a positive document, the correct useful document. Then we have a hard negative document, a confusing document that looks related but does not actually help. And why we use this? So the ReasonIR paper trains the retriever with contrastive learning. So with the help of contrastive learning, it is helped to reject those documents which does not have meaningful information in it. So this is very important concept for all of us to know. Then the retriever learns query should be close to the positive document and query should be far from hard negative document. So this is what the retriever learns out of this training examples. So we've provided certain query, then we provided some positive documents, then some hard negative documents, then another query, positive documents, hard negative documents. So these are the training data which is used in order to train this model. Okay. Now, then we perform query rewriting. So query rewriting expands a short user question into a richer query. So why we use this? Because the reasoning questions may not contain the exact words used inside the useful document. So user asks, why do night shift workers sleep badly? So useful document may talk about, circadian rhythm, body clock, sleep cycles, sunlight. So rewriting helps the retriever search for hidden concepts. So in the real ReasonIR paper, an LLM rewrites the query. Here we use a simple rule-based rewrite. So here is the rewriting query, function which we have mentioned. So rewrite the original question into a richer retrieval query. You can in fact integrate an LLM like ChatGPT or Gemini or Claude in order to have your LLM query rewriting done. Okay. So with this, once we have written this, we took some arguments like the query, which has the original user question, and we return a more detailed query for better retrieval. And then that the rewriting is done. So the reasoning query is given, and on the basis of that reasoning query, we retrieve the documents that explain the hidden concept behind the question, the background knowledge needed, the cause-effect relationship, the theory that helps answer it. Okay, so this is how the query rewriting part is done. Then we perform basic ReasonIR style retriever implementation. So this class does the main retrieval work. It handles loading the embedding model, converting documents into vectors, converting user query into a vector, comparing query and document vectors, and returning top matching documents. So why we use embeddings? So computers do not understand raw text meaning directly. So embeddings convert text into numbers, and similar meaning should have similar vectors and close vectors. Okay, the distance between those vectors are comparatively closer with respect to relevant meanings of context or text. So here we implemented the class ReasonIR basic retriever. We have initialized, we have written an initializer with some documents and the model name. So model which we are taking is sentence transformer, all mini LM L6B2. So this initializes the retriever where we take the document, list of documents to search from, and a model name. This is the embedding model name, which we are going to use to convert, raw text into embeddings, into numerical arrays. The model which we are using is all mini LM L6B2, which is a small and a fast model. It is a good model for basic local demo, which we can do. Then we took documents, we took this model, then we got so a complete set of document texts. So here we are going to read the full text, and we're going to append those texts, and then we are going to encode all of these documents. So in order to perform encoding of these documents, what are we trying to do? So we convert documents into embeddings. So documented embeddings can be created once and reused for every user query. So given a set of documents, you are going to perform a document embedding on the complete document set. So this is how we can do it. We can use this model.encode function. Within that model encode function, we can pass document text, and we can enable this feature, normalize embeddings equal to true, which means you're going to have normalized embeddings. Okay, the data is normalized, which means it is represented on a common scale. Normalization techniques like min-max scalar is applied to it. And similarly, your document embeddings, mathematical metrics would be created out of the documents. Okay. Then we have defined a retrieve function where we are going to have an input as query. We are going to filter top 3 documents, and we are going to perform user query rewrite. So we are going to retrieve top k useful documents. We'll take a user question, number of documents to return, and whether to rewrite the query. And then we are going to get a list of retrieved documents with scores. So this is what we are going to get. So now what next we are going to do? We are going to rewrite the query if enabled, and a richer query can help find reasoning documents. So we are going to rewrite the query, whatever query is given, and we are going to get a final query returned out of it if that is true. So we are going to convert this query into vector embedding now, and we need a query vector to compare with document vectors. So I'm going to use model.encode. I'm going to take the final query. I'm going to normalize those embeddings, and I'm going to save that into query embedding. So now you can see that we have got these 2 important variables. One is this query embedding, and above we have got the document embeddings. Okay. So these the documents embeddings. Okay. These are the 2 important variable which will help us calculate the cosine similarity and see for every specific query which documents matches closely. Now, so once we are done with this, after getting query embeddings, now we are going to calculate the cosine similarity. So higher the score between the query embedding and the document embedding, more similar the meaning would be for those documents. So we are going to calculate this cosine similarity. We're going to call this function cosine similarity, and we are going to pass query embedding and the document embeddings, and we are going to fetch the score of the comparison of that respective documents. And then we are going to sort those documents by score. Okay. So we are going to use numpy.arg sort, which gives low to high order. And we are going to use this, slicing mechanism, which will change it to high to low. And this will keep only top results, top 3 results, whatever number of results are required. So we have implemented argument sort. Then we changed it to high to low, and then we filtered the top k records, and similarly we got the ranked indices. Okay, and finally we got to prepare the output results. So out of these ranked indices, we are going to fetch the index of each document. So we are going to fetch the ID, title, text, and score of that particular document, and finally we are going to print the results. Now, on step number 5, you're going to implement a simple RAG answer generator. So this RAG means retrieval augmented generation. In a real RAG system, we are going to retrieve useful documents. We are going to send question plus documents to an LLM, and the LLM generates the final answer. So here we are not calling an LLM. We simply show the top retrieved document as the answer. And this keeps the implementation simple and easy to understand. So a RAG can communicate with LLM to regenerate the answer. And we'll talk about LLM implementations also in the upcoming sessions. Okay. Now, so we are generating an answer. And in fact, we are just returning the document. So we are going to use the question and the retrieved doc. We are going to generate a basic answer using retrieved documents, where the argument is an original user question, the documents returned by the retriever, and a simple RAG style answer string that would be returned. So we are going to combine retrieved documents into one context block, and in production, this context is passed to an LLM. Okay. So here we are going to retrieve those documents. For each document, we are going to find out its text, and we are going to, append that document part into the context. And once the context is ready, we are going to filter that document, and out of that context we are going to print it. So we print the question, we print the context, then the basic RAG answer is implemented. From that document, the title would be extracted, and for the explanation, its text from the document would be extracted, which we have created above in the JSON. Okay. Now, finally, we are going to test the implementation. So this block runs only when this file is, executed directly. So this allows the file to be used in 2 ways, where we can run it with, Python ReasonIR basic.py, or, any way like that. But I'm on a Jupyter notebook, so I'm going to quickly run this cell, and I'm going to run it. So under the main function, what I have done, so I've called this class ReasonIR-basic-retriever, where I have passed the documents, and we got a retriever in return. Then we have given him some, sample queries which we wanted to test. And then we printed the basic retriever, responses. So for sample queries, we fetched each query, we printed that query. Then we, displayed that query. And then using that retriever object, the retriever class object, which we created above, we are going to fetch retriever.retrieve, and we're going to pass the query, top k documents, and, whether you would want the user query rewriting to be true. And similarly, we are going to get the retrieved docs. Okay. Now, once these top documents are retrieved, we are going to, display that doc title and score of that document. And finally, we are going to generate an answer on the basis of the query and the retrieved documents. And finally, the answer would be generated. So this is how the overall RAG is implemented. So here you can see, once we run this typical code, it will, perform, all these, training part. And once these document encodings are complete, then here we have these queries where suppose we have given the system this query, why do night shift workers struggle to sleep during the day? So we got some documents like circadian rhythm, and we got the cosine similarity score, and the cosine similarity score is 0.46% for this. And then we also got RAG generation, which has 0.22, which means this is far and this is close. And since this is close, it is more meaningful. So that document is extracted and a RAG answer is generated. So we retrieve the context from that document, and then we have displayed the title of that document, and then we have displayed the text of the document as a generated response. Okay, so this is how a RAG is implemented, and the ReasonIR RAG is implemented, inspired from Meta, ReasonIR model. So here you can go to github.com/hack with us /Meta ReasonIR, and this is what we are going to evaluate and plan. Now, I also would like to evaluate it in my career OS about how does it matches with a production grade software, and whatever the fixes are, we are soon going to fix those and modify the code file with an expert level analysis. So once you guys are done with your code, you all can show, and we can scan the code and have a complete understanding. So I'm going to review it as a generative AI interviewer, and he is evaluating this code for a generative AI engineer, let's say, generative AI engineer. And let's say I'm going to say we're going to evaluate it with, let's say, a 1 to 3 years of experience is good, because this is a basic basic RAG implementation which we did. Okay. And we are going to evaluate it on the basis of project architecture, code correctness, role alignment, GenAI API integration, database backends, security, error handling, edge cases, testing, deployment readiness, code ownership. So I'm going to evaluate it on the basis of project architecture, code correctness, role alignment, GenAI API integration quality, GenAI integration quality. Okay. Then, so we don't have a database backend or data handling quality. Let's say I will do data handling. Security, secrets, and input validation. I don't have used any secrets, so I'll just do security and input validation, error handling and edge cases, testing, documentation, deployment readiness, and code ownership. So this is what I'm going to scan. And eventually we can, let's say, take it to 5+ years of experience. Let's say how professionally a production grade, code must be written for this. So now I'm going to evaluate this for you. I'm going to scan the project. And let's see what response do we get. And once we get those fixes, we are going to convert this code into a production grade code and post this code fixes. So you guys have to implement these, code fixes, and then use it in your resume and show confidently about how you can implement a RAG, however it is implemented, like organizations at Meta, and how you can help organizations implement RAG systems accordingly for different problem statements and use cases. So let the analysis be done. Okay, great. So now the evaluations are done. Okay, great. So I think with the Meta ReasonIR, we have evaluated this. One file was scanned, and let me just minimize the size a bit. So here we say the AI assistance risk is 61%. So we have to reduce the AI assistance risk, and it should be less than 30%. Overall score is around 57%, which needs to be improved, and 43% is the readiness. So even though this code was written inspired through Meta's basic implementation, but when we have to deploy it at production, we do have to implement some more stuff. And what is that we are going to review and implement? So this repo demonstrates a decent conceptual understanding of semantic retrieval and ReasonIR style ideas, but it does not yet provide enough evidence of senior level generative AI engineering capability. It is best viewed as a tutorial quality prototype rather than a production capable GenAI project, that is for sure. So you guys have to implement this tutorial into a production capable GenAI project. That is what is your objective. Then here are the rubrics. So project architecture modularity is 53. Code correctness and working logic is 60. Role alignment with target job is 60. Then GenAI integration quality is 40. Data handling quality is 50. Security and input validation is 50. Error handling edge cases 40. Testing and documentation 70. Deployment readiness is 40, and code ownership and AI assistance risk is 60. So these all needs to be improved. Here is the architecture of the code. So here we detected, a single Jupyter notebook with Meta reason.ipynb. Here are the issues which we need to fix. So now the fix is project is a notebook demo rather than a production grade GenAI system that needs to be implemented. So we have to refactor into modules for ingestion, validation, embedding, indexing, retrieval, generation, evaluation, and service serving. We have to add configuration, logging, and deployment artifacts. These fixes are required. No real LLM backed GenAI integration is shown. So we have to add a pluggable generation layer, which means an LLM integration has to be done with explicit prompt templates, source grounding, citations, fallback behavior, and evaluation of answer quality. So that we have to fix. Then it has weak input validation and data scheme handling. So we have to introduce document and query validation. We have to enforce schemas. We have to reject invalid records and add normalization and deduplication steps. That needs to be added. So while you are implementing such style of RAGs, make sure that you incorporate all of these fixes in your project so that your project looks like a production grade system. Okay. Then we have minimal error handling for model and retrieval failures, where we are going to wrap model initialization and retrieval operations in actionable exceptions, validate parameters, and add fallback or recovery path. Similarly, no testing or retrieval evaluation harness. So we have to add tests for schema validation, retrieval correctness, edge cases, and small benchmark suit with retrieval metrics. And similarly, we have query rewriting is simplistic and may inject noise. So we have to make rewriting conditional, compare against a no rewrite baseline, and evaluate learned or LLM based rewriting with metrics. Okay. So these are the missing items which needs to be implemented, and these are some of the security concerns. Then there are some interview questions which we are going to take up once this project is ready, the implementation is done. Okay. So these questions we are going to take up in the upcoming sessions. So I hope you guys got a clean idea about how a RAG is implemented, how a ReasonIR RAG, which performs well, has certain metrics to be accounted. We discussed all of that, and then we got an implementation on IPYNB for you to get started with RAG implementations. And then we are going to make these RAG implementations into a production grade systems. Thank you guys so much for watching, and stay tuned and keep preparing with the Talent Grid 90-day interview preparation programs. And you can get started today. Book your slot and get started today. Have a great day.